Hello, Matthews Gatos here. We're going to do probability lesson number 3, which is mutually exclusive events, or the events A union B, which you remember from previous units is OR. So we're really looking at OR probabilities. So the events A or B, those are inclusive because it can be A or B or both. OR in math is inclusive. A intersect B, that is exclusive. That is the and or the overlap. So we're going to investigate what happens when we have inclusive use of or and the exclusive use of and. Let's look at investigating mutually exclusive events. So let's say I have a die, I roll the die, and I'm going to classify my events as either rolling an even number or rolling an odd number. So here are my 6 numbers of a die. Let's categorize them as either even or odd. So 1 is odd, 2 is even, 3 is odd, 4 is even, 5 is odd, 6 is even. So event A, everything in circle A, you can see are the numbers 2, 4, 6. The odd numbers in circle B here, 1, 3, and 5. Here's the inclusive use of the word or. So A or B. So all the ones in A or all the ones in B or all the ones in both. Well, you can see there's no overlap. So actually the set A and B is the empty set. The or is 1, 2, 3, 4, 5, or 6. Now let's look at all of the numbers in each of these sets. So the number in set A, there are 3 in set A, which makes the probability 3 ways out of a total of 6. The number in set B, there are 3 outcomes in set B, so the probability of B happening would be 3 out of 6. A or B, there are 6 outcomes in A or B, so the probability would be 6 out of 6. And there are no outcomes in A and B, so the probability there would be 0 out of 6. Now we can put all of these in lowest terms. So 3 out of 6 in lowest terms is a half. 6 out of 6 is 1, so it's a 100% chance. And 0 out of 6 is 0, so it's a no chance. So I want to verify the following here. So verify that the number in A or B is equal to the number in A plus the number in B. So the number in A or B was 6, and that's equal to the number in A plus the number in B. That's true. I want to verify this probability as well. The probability of A or B was 1, and that's equal to the probability of A plus the probability of B. That's also true. So I know that those are true for mutually exclusive. Now, if A and B, the number in A and B, was not equal to the number in A and the number in B, I would know those events would not be mutually exclusive. There would be some overlap. So let's look at non-mutually exclusive events. So same idea with the die, but now we're going to categorize our events into even numbers for event A and multiple of 3 for event B. So let's just go through them all one at a time again. So number 1. It's not even, it's not a multiple of 3, so it goes on the outside. 2 is even. 3 is a multiple of 3. 4 is even. 5 is not even, it's not a multiple of 3, so it goes on the outside. 6. Now 6 is even, but it's also a multiple of 3, so I'm going to put it in the middle because it's true for both. So in event A, my circle here, 2, 4, and 6, 3 events, which makes my probability for event A 3 out of 6. Event B, right here, event B is the multiples of 3, so the numbers are 3 and 6. There are 2 events, which makes my probability 2 out of 6. Now A or B, or being inclusive, it's all the ones in A or all the ones in B or all the ones in both. So that would be the 2, 3, 4, and 6. So 4 outcomes, the probability would be 4 out of a total possibility of 6. A and B, that's the overlap right there in the middle, which is 6. You can see there's 1 element there, so the probability would be 1 out of 6. Now for these fractions here, I'm just going to put these in lowest terms, a half, a third, and 2/3. Okay, so let's look at this now. So again, before we did, the number in A or B should be equal to the number in A and the number in B. So the number in A or B was 5. There are 3 in A and 2 in B. No, there we are. A or B. 1, 2, 3, 4. Let me try that again. Sorry, 4. 4 in A or B, 3 in A, 2 in B. And you can see that 4 is not equal to 5. The reason is because there is an overlap. So I need to subtract the overlap. So the new formula really becomes the number in A, which was 4, is equal to the number in A, which is 3, plus the number in B, subtract the number in both, and then that would be equal. So using that idea, let's look at the probability statement. I know for sure this is not true. The probability in A or B is not the probability in A plus the probability in B because I have that overlap there. So I need to change this formula to be like this. So the probability in A or B would be 4 out of 6, and that should equal to the probability in A, 3 out of 6, plus the probability of being in B, 2 out of 6, subtract the probability in both. So in doing that, 3 plus 2 is 5, take away 1 is 4. I now know it's true. So the big thing here is to always subtract that overlap in the middle. So how do you know if there's overlap or not? Well, mutually exclusive events have no overlap. Non-mutually exclusive events have an overlap. So all you have to do is ask yourself, can both happen at the same time? If the answer to that question is no, both can't happen at the same time, meaning there is no overlap, the probability of A or B is the individual probabilities added together. Now, if both can happen, that means there is overlap. And if there is overlap, we must always subtract that overlap. So let's practice just categorizing as mutually exclusive or not. So can both events happen? So we're rolling a die. We're looking at even numbers and odd numbers. So can a number be both an even number and an odd number? They can't be the same at the same time. So these are mutually exclusive because both cannot happen at the same time. It can't be even and odd at the same time. Now, not only are these mutually exclusive, these are also complementary events because either it's even or it's not even, which is odd. Okay, next one. I'm drawing a card from a deck of cards. I want to know the events are face card and club. So can a card be both a face card and a club? And the answer to that question is yes, they can be both. So these are not mutually exclusive. There are those 3 cards right there that are face cards and clubs. Okay, next event. I'm throwing 2 die, and I want to look at having the die show the same value, which is doubles, or having the total score be 11. So back up here, can both events happen? Can you get a number that is doubles and 11 at the same time? Well, let's look at the die. On the diagonal, these are all the ways of getting doubles. If you add these up, none of these add to 11. So can both happen? No, these are mutually exclusive. Let's go back to that idea of complementary events because this is an important observation. All complementary events are mutually exclusive. That is always true. However, the reverse is not always true. Not all mutually exclusive events are complementary. Okay, let's look at class example number 2. So we're going to look at these events and we want to pick out which ones are mutually exclusive. So in other words, which ones have no overlap. So let's start with A face card. Can a card be a face card and a red card at the same time? Yes, there's 6 red cards that are also face cards. Can a card be a face card and a club at the same time? Yes, because look here for the clubs. There are face cards right here that are clubs. Can a card be a face card and an ace at the same time? No, they can't. So those are mutually exclusive. And can a face card be a black card at the same time? Yes, there are 6 cards that are face cards in black. Okay, let's go to red cards. Can a red card also be a club? No. Can a red card also be an ace? Yes, there are 2 of them. Can a red card also be a black card? No. So B and E. Okay, let's go to clubs. Can a card be a club and an ace at the same time? Yes. Can a card be a club and a black card at the same time? Yes. So C doesn't work. Let's go to D. Can a card be an ace and a black card at the same time? Yes. So there are 3 events that are mutually exclusive. Which one of these are complementary? So are all cards face cards or aces? No, those aren't complementary. Are all cards red cards or clubs? No. All cards are either red or black. These are the ones that are also complementary. Okay, class example number 3, we're going to do the same thing but with pictures. So we're trying to find out which ones are mutually exclusive, having no overlap. Well, you can see A is all by itself, so it is mutually exclusive with everything because there's no overlap. B overlaps with C, but doesn't overlap with D. And then C overlaps with D, so that one's not. Okay, so we have some probability statements here. We want to determine based on the probabilities, are these mutually exclusive or not? Well, if they are mutually exclusive, there's no overlap. So the probability of A or B will equal to the probability of A plus the probability of B. Well, to know if this is true, I just have to add this side here or put it into my calculator. So 1/4 plus 1/3 is 7/12. So they are equal on both sides, which tells me they are mutually exclusive. Let's look at class example number 5. So we're drawing a card from a deck of 52, and I want to, using formulas, determine the probability of, first one, 9 of diamonds or a heart. So looking at the deck of cards, there is no overlap. 9 of diamonds and hearts, there's no overlap. So these are just the individual probabilities added together. So probability of picking a card out of the deck being diamonds, there's 1 9 of diamonds out of 52. Hearts, out of the 52 cards in the deck, 13 of them are hearts. So I can add those together on the calculator and put them into lowest terms, and I get that the probability is 7 out of 26. Okay, next one. I'm not looking at a 9 of diamonds, I'm just looking at a 9. So I want to look at the probability that a card is a 9 or a heart. So looking at my cards, you can see there is overlap. There is one card that is both 9 and heart. So it's been counted twice. So I need to subtract the overlap. So the probability of picking a card from the deck and it being a 9, 4 out of 52, plus the probability of picking hearts, 13 out of 52, subtract the one that is a heart and a 9 at the same time. I'm just going to change that to a 9. So subtract the probability of a heart and a 9 at the same time. That's that one card out of 52. So let's put those into my calculator. 4 out of 52 plus 13 out of 52, subtract the 1, and I get a probability of 4 out of 13. Okay, class example number 6. Blocks of different shapes and colors are placed into a bag. 3 cubes, blue, red, and green, 2 pyramids, red and yellow, 5 cylinders, blue, yellow, and 3 red. So I've listed that off on the side there. There's 10 altogether. So I want to know the probability that a block selected at random will be a pyramid or a cube. So can I be pyramid and cube at the same time? No. So these are mutually exclusive. There's no overlap. So the probability of the shape being a pyramid is the 2 pyramids out of 10, plus the probability of being a cube, I should say cube, not cylinder, probability of it being a cube are the 3 out of 10. So add those together, put them on my calculator, and I can do that on lowest terms, and I would get 1/2 in lowest terms. So 2 out of 10 plus 3 out of 10 is 5 out of 10. In lowest terms is 1/2. Okay, next one is the probability that it will not be red. So complementary event, it'll not be red. So let's take out all the reds and count how many are left. So I don't want reds. So I take out all of the reds and I'm left with 1, 2, 3, 4, 5. So 5 out of 10, or 1/2 of the shapes are not red. Okay, next one says it'll not be red or a cylinder. So can you have something that is not red and a cylinder at the same time? Well, yeah, you can look here. There are two shapes that are not red but are also cylinders. So these are not mutually exclusive. So we're going to look at the probability that it being red or a cylinder. So the probability of it being red is 5 out of 10. The probability of it being a cylinder, up here I had 5 cylinders, 5 out of 10. Subtract the red cylinders. So there are 3 out of 10 that are red cylinders. So you can add those together, just simply put them into your calculator, and in lowest terms you get 7/10. Okay, last example here. Tom and Andrew were asked to solve the problem. They're going to solve it in 2 different ways. We're going to figure out both ways here. So we have 200 people with symptoms, including headaches, backaches, participating in a study to see if this pain relief medicine works. All the people took the medication. The results are as follows. So 90% experienced headache relief, 126 experienced backache relief, 36 people experienced relief from both. So since there is a both there, I know that there's overlap, which means they are not mutually exclusive events. Okay, so Tom decided to solve the problem, and the problem is, what is the probability when you take the drug you're going to get relief from at least one of the 2 symptoms or neither of the symptoms? So what Tom did is he wants to use probability. So he said the probability of getting relief from a headache is 60 out of 200, or 0.3. The probability of backache, I can see there's 126 out of 200, as a decimal is 0.63. The probability of both is those 36 people. 36 out of 200 is 0.18. So the probability of getting relief from at least one of the 2 symptoms, at least, is a minimum. So it's going to be the probability of getting relief from headache or backache, or the probability of both. So I'm going to take the probability of getting relief from a headache, add it to the probability of getting relief from a backache, subtract the people that got both. So probability of getting relief from a headache, 0.3. Probability of getting relief from a backache, 0.63. Subtract the probability of both, 0.18. So I can just put those into my calculator to figure out the answer. And it looks like 75% of people got relief from at least one of the 2 symptoms. The next question says neither symptom. How many people, what's the chance that they had relief from neither? Well, this is a complementary event because here you have headache, backache, or both. This one here, all that you're left with is neither. So these are actually complementary events. So the probability of neither is 100% or all minus the probability of at least one. So I know that there are 25% of people that got relief from neither. So this is one way of doing it with probability formulas. Let's look at another way of doing it. So Andrew did it as a Venn diagram. So he said, okay, I know that 36 people received relief from both. So he put 36 people in the middle out of the 200. There's overlap. Now, 60% of people got relief from headache. So this whole headache circle has to add up to 60. So 60 minus the 36 there, 24 for headache only. For backache, that has to add up to 126, but there's already 36 in there. So 126, take away the 36, 90 people got relief just from the backache. Now this has to add up to 200 people. So on the outside, I take 200 and I subtract all of the ones on the inside to get 50 for neither. Now, let's answer the probability question. So Andrew does all the hard work with the Venn diagram, making the next part easier. Tom did all of the work as he went along, so he didn't have to do it up front. So getting relief from at least one symptom would be headache, backache, and then I would subtract for both. So I'm going to add those together. or sorry, at least one of the symptoms, headache, backache, or both. So headache, let's add those together. So headache would be the 24 people right here, 24 from headache. I could get relief from backache. So that would be my 90 people right here, 90 out of 200. And then I could have relief from both, which would be the 36 out of 200. So one or the other or both. Putting those all together in the calculator, I get 3 out of 4, which is the same as what Tom got, 75%. The ones that got relief from neither, that's those guys on the outside here. So for neither, I can just say that that is 50 out of 200. And I can put that into my calculator, and I get a quarter, which is the 25%. Okay, so you can see two different ways of answering the same question. Really, it comes down to personal preference. So to summarize, probability of A or B is the probabilities added together if they are mutually exclusive. If they are not mutually exclusive, I must subtract the overlap. Remember that complementary events are also a subset of the sample space. So either something happens or it doesn't. A, for example, would be complementary if the number in A and the number not in A add up to the sample space. All complementary events are mutually exclusive, but the reverse is not true. So my question for you now at the end of this lesson is, why did the mutually exclusive events break up? And I hope if you were paying attention to the lesson, you know the answer already. Because they had nothing in common. Okay, you guys can go ahead and do the practice questions. The detailed solutions to these are on D2L. And that concludes the end of lesson 3.